Good morning, class. This is the interim lecture for 3323 in Hydrosystems, and this is going to be published under week 7B. In our last lecture, we went over hydraulic jumps. A hydraulic jump is when flow goes from supercritical flow, very fast and shallow flow, and then it goes into subcritical flow, a deeper and slower flow. And that transition is a rapidly varied flow condition called the hydraulic jump. So in our last class, we derived the forces of momentum, and we showed that with the momentum equations, we can solve for the downstream and upstream depths of a hydraulic jump. And then we can use the energy equation to compute how much energy loss goes across a hydraulic jump. Now, hydraulic jumps are important because it's a phenomena that we use in design. It's something that we use for energy dissipation. It's something that we use to get flow from a spillway from something very high in elevation to very low in elevation. Then we use a jump to dissipate that energy before we release it back into a stream or a canal. So let's continue going over the hydraulic jump, and we're going to do a design example. And in that design example, we'll use a sluice gate, which is a gate that moves flow or measures flow of water. It's very common in water resources. So let's go over the hydraulic jumps. Now again, a hydraulic jump is a very, very quick change between super and subcritical flow. We call this rapidly varied flow, RVF. Now there's different types of hydraulic jumps. There's a weak jump. We call this an ungular jump. And that's when the upstream Froude number is between 1 and 1.7. So that's an ungular jump. And you see up here on the right hand of the screen, this is characterized by a series of waves, what they call standing waves. And then we have a weak jump. So our Froude number is a little higher, 1.7 to 2.5, and that's the upstream Froude number. That's your supercritical flow. And then we call that a weak jump. And that's characterized by a smooth rise in the water going from super to subcritical flow. And then as we get higher and higher on these upstream Froude numbers, we get into an oscillating jump, which is very unstable. These are characterized as an unstable jump, and it's whenever your upstream Froude number is between 2.5 and 4.5. And then if we get past the 4.5, we get into steady and strong jumps. The steady jump is characterized by some as the best design jump. This means when we say best design, it means that we know we're going to fully form a jump and get subcritical flow downstream, and we know we're going to fully dissipate the energy across a given length of a jump. So the steady jump is typically what we look for in design. And then a strong jump, something higher than that, a Froude number higher than 9, is still, we're sure we're going to get a full hydraulic jump, but it's characterized by very choppy and intermittent waves. That's hard to determine the length of the jump. So the equation for upstream and downstream depths is shown here. And we derived this equation last time we were in our class in week 7A. So the downstream depth and the ratio of the downstream and upstream depths are a function of the upstream Froude number. If you look into a book called Chow's Open Channel Hydraulics, you can find this in section 15-2, and I'll be sure to post a link to that, to an open version of that book, so everyone can read those sections or review those sections. So here in these images, you can see a weak jump and a steady jump. A weak jump with just standing waves, or maybe an ungular jump, and then here into a steady jump where it's a fully formed subcritical flow. So how do we manage these jumps? We want to make sure that our jump happens in a place that we can control so that our structures don't fail. So one good reference for managing jumps is the design of small dams. And in the design of small dams published by the US Bureau of Reclamation, we have guidance to design stilling basins and aprons. A stilling basin is where we force a hydraulic jump. So here is a design of a side flow spillway. This is a dam embankment. And the water will spill through this concrete channel. And then we have to get that water down to the bottom of the embankment, which makes through the chute. And the chute is where we have supercritical flow, where a Froude number is greater than 1. And then we have chute blocks. These are chute blocks that start breaking up the flow. They start impeding the flow. And we offset those chute blocks with baffle blocks to force our jump. We start making the water have to hit and run into things so that that jump starts to happen. And then we have what's called an end sill. And at the end sill is where we let go of the water down into the next channel. And hopefully we've forced supercritical flow into subcritical flow. And we've managed to dissipate our energy within the stilling basin or the jump apron. This is an image of where we want to design the best performance. And as you can see, the best performance according to the design of small dams is between an upstream Froude number of 4.5 to 9. This graph is the length over the downstream height of the jump. And this is the Froude number. So it's also acceptable to have a strong jump, but the best performance is a steady jump. And again, if we're in an undulating and weak jump, we're not sure that we're going to get subcritical flow when we release that flow back into the channel. Another way to control the release of flow is called a baffle chute drop. Now, what a baffle chute drop does is something different. We have all these baffle chutes that are offset from each other, and that makes sure that you never get supercritical flow. So the theory behind the baffle chute drop is that you don't let a jump happen, that the water spills over into the baffle chute and you never get to supercritical flow. So your Froude number never goes more than 1. And so you eliminate the jump altogether. So that's another way to move water down a steep slope, is find ways to dissipate the energy the whole way down instead of having one stilling basin or apron where you dissipate that energy all at once. Another way to do it is certain outlet structures. So there's a type 4 outlet structure, and this is for large pipes. So here is a picture of a type 4, and this is a dam embankment. And outside of the embankment, there's an outlet works, and that outlet works releases flow really fast. Now, inside of the type 4, it's actually curved. The concrete is curved so that the water hits and the jump is all forced behind this concrete wall. So you get all this rapidly varied flow and turbulence just happening in one spot. And then you release it out here, and you can see this is calm subcritical flow because all the jump has occurred behind this concrete wall. So we can do it with outlet structures, basins, jump basins, aprons, and baffle chutes. So a good reference for these designs is hydraulic design of stilling basins and energy dissipators, by the US Bureau of Reclamation. The US Bureau of Reclamation has designed dams and embankments, outlet works for many, many years, and they have many, many good references on how to design for hydraulic jumps and how to design stilling basins. Another way that jumps happen is when we're moving water from a canal into a channel, and the opening of our gate is much smaller than the depth of the water above. What that creates is supercritical flow coming under the gate, and then at the other end of the gate, we have subcritical flow, And so between those two locations, we get a hydraulic jump. One common gate is called a sluice gate. So we can use a sluice gate to move water out of a canal. Sometimes you can use sluice gates to control outlet works over a spillway. So there's a lot of uses in water resources for sluice gates. And generally what happens, as shown in this very simple image, is the depth of the water above the gate is much higher than the opening. It produces supercritical flow. And if it's unimpeded at the bottom, you can either stay supercritical flow all the way, or at some point you get a jump. So let's go over an example problem of a sluice gate. We're going to have an upstream depth of 5 feet, and there's going to be an opening of 1 foot. So the sluice gate is opened 1 foot. The channel width is going to be 4 feet. And let's see what kind of jump we've formed and see how long that jump is. Then let's solve for the energy loss across that gate. So here are images from the design of small dams, and this is a coefficient of discharge for sluice gates. We also have a graph in our book that we can reference for our design problem. So I'm going to start setting up our problem on the whiteboard. So we have a sluice gate. Sluice gates usually have some sort of wheel or something that can turn them up and down. And then we have, we're going to assume a flat channel bottom. And the water on the upstream side is 5 feet. So we'll say y1 equals 5 feet. And the water goes through this opening. This opening is 1 foot. And then it has some sort of a jump that we don't know how big it is yet. And it goes into, we're going to call this y3, some unknown depth y3. Now in the book, they call this opening A. They use the small letter A. Some do it differently, but we can say A equals 1.0 feet. But I'm also going to call this y2. That A and y2 are the same. And then the channel has a base width B of 4 feet. It's 4 feet wide and it's a rectangular channel. So we can use our rectangular channel assumptions for the energy equation. Now the question is find, given the parameters, find the unit discharge, find the unit discharge Q. Find the downstream depth, y3, and then find the energy loss. Find energy loss. We'll call this E sub L. So if we go into our book in page 396, we have figure 10.19 and equation 10.3. So if we use equation 10.3, whoops, that's a 3, 10.3, says that the unit discharge through a sluice gate Q is equal to a coefficient of discharge times that opening A times the square root of 2G Y1. So we know Y1 and we know A. We don't know our coefficient of discharge. And if you look on figure 10.19, we can find C sub D by solving for y1 over a. So C sub D is some function of y1 over a. So y1 over a is equal to 5. A is 1, and the depth 1 is 5 feet. So y1 over a equals 5. And if we assume a free outflow, we can follow this graph on number 5 and get a coefficient of discharge. C sub D is approximately equal to 0.59. So now we have everything we need to solve for Q, for a unit discharge Q. So Q equals 0.59 times 1 foot for A times the square root of gravity, 32.2, times y1, which is 5 feet. And the square root goes all the way across y1. So Q equals 7.5 cubic feet per second per foot. So we found Q. Now to find the downstream depth, we need to look back at our jump equations. Right? Do you remember our jump equations where y1 equals y2 over 2? So the negative 1 plus the square root of 1 plus 8 times the Froude number squared. And that's the Froude number at location 1. So here y1 is actually going to be y2 or a, and y2 is going to be y3, because our supercritical flow starts at the gate. So we need to go from the gate, from supercritical to the subcritical section. So we need to know our Froude number. So the Froude number is equal to the velocity in this channel divided by the square root of gravity. And for rectangular channels, that's depth. So the square root of gravity times the depth. This can also be the unit discharge. I'll walk it through a little slower. V equals Q over A. The Froude number can then be expressed as Q over A times the square root of gravity times the depth at y2. And if we divide through by B, the base width of the channel, then the unit discharge Q is equal to y times the square root of gravity times y2. So this equals our Q, which is 7.5, divided by the depth at A, which is 1, times gravity times 1. If gravity is equal to 32.2, this equals 1.32 of a Froude number. So the Froude number is not very high, right? So this is a weak jump. This is a weak hydraulic jump. So how can we use this to find y3? Well, if we say that y2 equals y3 over 2, it's negative 1 plus the square root of 1 plus 8 times the Froude number squared. Actually, this would be a Froude number at 0.2. Actually, correction. Y3 equals Y2. So we want to solve for y3 because we already know y2, so correction. So then y3 equals 1 foot, because it's 1 foot deep, so 1/2 is -1 times the quantity of -1 plus the square root of 1 plus 8 times 1.32 squared. And that's all in the square root here. And that's quantity. So y3 is equal to 1.4 feet. So we only went up not even half a foot from the opening to y3. We now know that this equals 1.4 feet. Now there's some energy loss across the gate and across the jump. So up here we have our energy grade line. We have our energy grade line up here. And then somehow we lose, or not somehow, we lose our energy through the gate, through the opening, and then we lose energy through the jump. So that difference in energy is the energy loss across the gate and the jump. So how would we find that? So the energy loss is going to equal the total energy at E1 minus the total energy at E3. So whatever the energy is up here compared to the energy down here is how much energy we lost going through the gate, which has some coefficient of discharge. It has contraction losses, and then across the jump. So most of the losses on this problem are probably going to be through the gate because our jump isn't very large. Our jump had a Froude number of 1.3, so it was not a very strong jump. It only has a subsequent depth of 1.4 from 1. But let's find what the total loss is. So the energy loss in a rectangular channel is q squared over 2g y1 squared plus y1. And that equals 7.5 squared divided by 64.4 times 5 feet squared plus 5 feet. And that equals 5.03 feet. So most of our energy is stored in the potential energy. There's not a lot of velocity head in the backwater of the gate. And that seems to make sense. So energy 1 is 5.3 feet. And then our energy after we get through the gate and across our jump is equal to the unit discharge 2g y3 squared plus y3. And we're assuming continuity. So our unit discharge at both locations is the same. It's steady flow. 64.4 times 1.4 squared plus 1.4. And if we calculate that out, our energy is 1.84 feet. So the energy loss is then the difference in energy from upstream of the gate, E1, to the energy the downstream, E3. And so that difference is 3.2 feet. So I think we found our problem. We've solved our problem. The unit discharge is 7.5 cubic feet per second per foot. The downstream subsequent depth of the jump is 1.4 feet, and we solved that using our jump equations. And our energy loss across the gate and the jump is 3.2 feet. So using our equations of momentum, we can solve for a jump. Using our sluice gate discharge equations, we can solve for the sluice gate. And then using our energy equations for rectangular channel, we can solve for the energy lost across the gate and the jump. Now, what is 3.2 feet of energy loss? Is that a lot, a little? How much is 3.2 feet of energy loss? Is there any way to quantify that in something, some kind of a unit that we would be able to better understand? So again, we have our ground, we have a gate, we have water going to that gate, coming out of that gate through a jump, and across this gate and the jump, we have 3.2 feet. Change in energy equals 3.2 feet. So let's see if we can put this in something that we better recognize and better understand. So if my energy loss is 3.2 feet and my channel width is 4 feet wide, that means over that loss, so E sub L times B would equal our energy loss of 3.2 feet times 4, which equals 12.8 feet squared of energy loss. Now the length of this jump, L sub j, according to published literature, the length of a jump, L sub j, is some function of the subsequent depth, which is r's y sub 3, which is somewhere between 4 and 6. So the length of our jump is somewhere between 5.6 feet and somewhere else between 8.4 feet. So let's say that our length of our jump is between these two. Let's say it's 7 feet. We'll just take the average of the smallest and largest it can be. So the length of the jump is 7 feet. So if I get all of this energy loss into cubic feet, I can say that the energy loss times the length of the jump times the width of the channel is going to be in cubic feet. That equals 89.6 cubic feet. And the reason I want to get it into cubic feet is because we have water. We have an incompressible Newtonian fluid of water where the unit weight of that water is equal to 62.4 pounds per cubic foot. You can see where I'm going now. 89.6 cubic feet of loss across the jump and the gate times 62.4 pounds per cubic foot gives us pounds, which equals 5,591 pounds of energy loss. So now we're starting to look like there's a lot of energy loss across here. Even for a weak jump, we're burning up a lot of energy. Or if you turn this into tons, we can say this is 2.8 tons of energy loss across the gate and the hydraulic jump. So even for a very small jump and a very relatively small flow rate through the gate, only a 1 foot opening, if we go by the jump length and get it into cubic feet, get our energy loss into cubic feet, that's a lot of loss of energy. 2.8 tons of energy lost just going through the channel. So we've solved a problem using our hydraulic jump equations, the sluice gate equations, and we've solved for how much energy loss goes across a jump and a gate. So this is covered in page 396 of your book, and there will be some homework on these example problems after we get our homework in from the last lecture, which we're gonna have due the Wednesday after this coming Wednesday. So please watch this video. This is gonna be a great test question, sluice gate and a hydraulic jump, and how much energy loss do we lose across the jump? And again, this is still assuming a frictionless channel. We haven't even accounted for our losses due to friction in the channel, which we're gonna get to soon. So thank you for watching. I hope this lecture makes sense. I will post this onto YouTube and I'll put a link. And then this whiteboard will be in week 7B. And again, thank you for watching. I will see everyone on Wednesday, and have a good rest of your day.